Hello everyone, welcome to the course on computer aided drug design. Today we are going to talk about quantum mechanics. Okay. So, we have been talking about molecular mechanics quite a lot, molecular mechanics also known as force fields. So, what does it do? Molecular mechanics, just to recap, nuclei and electrons are lumped into atom like particle. So, you do not differentiate between the electrons and the nucleus. So, we do not see electron repulsion, nucleus electron attraction and so on. So, they are based on the springs and classical potentials. Hooke's law comes into picture. So, if the bond length is extended delta x, then the bond energy associated will be proportional to delta x square, okay, and so on actually delta x square. So, we can use it for calculating the structure, we can do some diffusion properties, dynamics, we can look at total energy, okay, we can look at free energies, diffusion coefficient and so on. So, we cannot do those which are related to the electronic property. Then we looked at different functional forms of force field, okay, different functional forms. I showed you MM2, I showed you so many different MMFF and so on. So, there were force field with delta x square, delta x raised to the power 4, e raised to the power delta x and so on. And then there are a lot of parameters in this force field. So, they all depend upon the atom types, okay. Atom types means a carbon can have different environment and different bonding, right. You can have carbon single bond, carbon sp3, carbon double bond, carbon sp2, carbon triple bond, carbon sp, okay, and then carbon in the aromatic, carbon in a 5-membered okay, 5-membered ring form and so on. So, different types of carbon. Similarly, carbon oxygen, different types of carbon oxygen. You can have ketonic, you can have ether type, ester type, inside a 5-membered aliphatic, an aromatic form, so many things. So, we had parameters for all of them. Then the boundary conditions, what type of boundary conditions, is it vacuum, is it surrounded by solvents, is it in a periodic box. Then came the geometric optimization, this is very important. So, we want to find out the minimum energy conformation of the molecule, okay. So, that is energy minimization, we use lot of numerical techniques to calculate the minimum energy, okay. So, because mostly thermodynamically they occupy the minimum energy, and of course, I also mentioned that it is not that all the molecules will be at that stage, it will be get distributed based on the Boltzmann equation. So, you may have some molecules at slightly higher energy and so on, actually depend upon the difference in the energy levels from one state to another. So, this is called the molecular mechanics. So, everything is lumped as atoms connected by springs and so on. Now, let us go to something different, that is called the quantum mechanics. Here nuclei and electrons of the molecules are separately considered, okay. So, that is very important, they are separately considered. There are two different approaches, one is called the ab initio, other one is called the semi-empirical. Ab initio is very rigorous, it is based on first principles, okay. There are no stored parameters or data, so it takes much longer time. So, ab initio calculations are done only for few atoms, whereas semi-empirical contains a lot of stored parameters, it has got some empirical equations, relationship, it is less accurate and it can be used for larger molecules. So, it is much more practical for drug discovery like our area. So, it is more approximate than ab initio, but we can go to hundreds of atoms, okay. So, what are the use of these quantum mechanics? We can use molecular orbital energies, we can look at partial charges, we can look at electrostatic potential, we can look at dipole moments, we can look at bond formation, energy required for bond formation, energy required for bond breakage, okay. So, all these can be done, bond formation, breakage. So, all these calculations can be done using molecular quantum mechanic theory. Okay. So, we can look at molecules at different oxidation states. So, all these can be done in quantum mechanics, and we will look at the semi-empirical, okay, which is faster but less accurate, ab initio, which is very rigorous based on first principles. Okay. So, they are all based on Schrodinger's equation. Electrons are considered as wave like particles whose waviness is mathematically represented by a set of wave functions. Okay. So, it addresses based on the Schrodinger's equation. So, where are the electrons and nuclei in space? So, that you can find out from the configuration, conformation, size, shape and so on actually. And the energies, we can do heat of formation, conformational stability, chemical reactivity, spectral properties, etc. So, we can even simulate different types of spectra using quantum mechanic calculations. That is advantage, we can simulate different types of spectra. Okay, so quantum mechanic methods are based on following principles. Nuclei and electrons are distinguished from each other. So, you have electron nuclear interaction. So, you may have here attractions, here repulsions. So, you do not consider all the electrons because that will be too much. I will tell about how they are sort of averaged out. Interactions are governed by nuclear and electron charges, okay, that is the potential energy and then electron motions. So, the interactions determine the spatial distribution. So, we can, if you want to find out the size, shape of the molecule, these are all determined based on nucleus and electrons and their energy. So, nuclear repulsions, electron repulsions, nuclear electron attractions and so on. So, that is what quantum mechanics methods are based on. Okay, so like I said, we have the ab initio, we have the semi-empirical. Ab initio is limited to tens of atoms. Okay, so you need to have very good computational resource. So, we can apply it for organics, organometallics, molecular fragments, catalytic components of an enzyme. We can also do vacuum, we can do implicit solvent, can be used to study ground state, transition state, excited state. Okay, there are methods. So, there are softwares called gammas, Gaussian. So, all these names you will come across if you are interested in looking at ab initio type of method. So, if I want to really calculate what are the energies like this, so we can calculate energies at these various states very accurately using ab initio method. Semi-empirical methods, ab initio tens of atoms, we can go to hundreds of atoms or even larger. So, as I said before, if you are looking at thousands of atoms, we will not go for quantum mechanics, we have to go for molecular mechanics. Okay. So, limited to hundreds of atoms can be applied to organics, organometallics, oligomers, small peptide, nucleotide, saccharide. So, we can do semi-empirical method. We can look at again ground state, transition like this, excited states, but of course, this will be less accurate unlike the ab initio. If you really want to look at the small changes, if you have different enantiomers, I would not recommend this, I would recommend ab initio method. So, many software, many semi-empirical methods you will come across, AMPAC, MOPAC, ZINDO, AM1, PM3, all these are semi-empirical methods which you will use as you go along. Okay. So, two basic methods like this, generally for drug discovery this is good enough. If you are a theoretical chemist, okay, then you may go into ab initio methods. Okay, so you need to understand certain terminologies. The most important in ab initio is called basis sets. This is a set of one electron wave functions used to build the molecular orbital wave functions. Okay, basis set means is a one electron wave function used to build molecular orbital wave function. You also have minimal basis set, that is which only occupied orbitals of each isolated atoms are used to compose. Okay. So, unoccupied orbitals are called virtual orbitals. So, only minimal basis set is only the occupied orbitals are considered. Okay. We do not consider the unoccupied orbitals. okay, that is called the minimal basis set. Okay. So, generally if you want to go into ab initio, it is good enough to go with minimal basis set because it does not consider the unoccupied orbitals, then the calculations are too much to do. There are many approximations when we consider the quantum mechanics. The most important one, we will talk about some of those approximations. The most important one is called the Born-Oppenheimer approximation. So, what it does is it decouples the electronic and nuclear degrees of freedom. Okay. So, it assumes the nuclear centers of mass are fixed, okay, and the electrons move around this nucleus. Okay. So, you reduce the number of degrees of freedom, that is the advantage of Born-Oppenheimer approximation. So, the wave function is parameterized with respect to the nuclear coordinates. So, remember that. So, it assumes that the nucleus is fixed, like we assume that sun is fixed and all the planets revolve around the sun. That is the easiest approximation. Okay. Although you know that sun also moves, then all the planets also move. So, the calculations becomes more difficult to do, but as a first approximation we can always assume sun is fixed, all the planets are going around. Okay. That is the advantage, okay, like that we can do that. That is called the Born-Oppenheimer approximation. Then comes Hartree-Fock approximation. So, as you know there are many electrons in each atom. So, you approximate it by a sequential calculation of the response of the ith electron in the average potential or rest of the electrons. This one electron operator is called the Fock operator. That means suppose there are many electrons, 20 electrons, and you are looking at the ith electron interaction with all the 20, it is going to be very difficult, right? Ith with 1, ith with 2, ith with 3, ith with 4 and so on, too many calculations. So, what you do is we take the average potential of remaining 19 electrons and then we look at the interaction of the ith electron with the remaining 19 electrons. So, the calculations come down dramatically, okay, number of interactions you look at comes down dramatically, and that is called the Hartree-Fock approximation. Okay. So, it makes life much simpler. Then comes anti-symmetric wave function. Wave functions describing electrons obey Fermi-Dirac statistics, that is they must be anti-symmetric with respect to an interchange of coordinates. So, this is called, a term of determinant is called the Slater determinant. So, we have the Born-Oppenheimer approximation which fixes the nucleus degrees of freedom, only the electron degrees of freedom are considered. Then we have the Hartree-Fock approximation where you look at the interaction of the ith electron with an average potential of rest of the electrons. Then anti-symmetric wave functions describing they obey the Fermi-Dirac statistics, that is they must be anti-symmetric with respect to an interchange of coordinates. Okay. Then we have the Ruthan equations, that is the Hartree-Fock equations are a set of coupled integro differential equations. Okay. So, that is called the Ruthan equation using basis vectors of Hilbert space. So, this can be transformed into a set of algebraic equations. So, this gives a generalized eigenvalue problem to us, because once you have an algebraic set of equations it becomes much easier for you to calculate. Okay. So, Hartree-Fock equation and so we have the Hartree-Fock SCF Hartree-Fock self consistent field, that is the self consistent field. So, this is the name of the procedure to calculate the charge distribution. The problem is non-linear, the Fock matrix is dependent on the variational coefficients that are being calculated. So, we need to have an iterative approach for self consistency. Then we have the post Hartree-Fock calculations. So, the Hartree-Fock calculation has a built-in deficiency, no electron-electron correlation, thus further work needs to be performed. So, lumped as post Hartree-Fock calculations, most of the schemes involve the diagonalization of large matrix. So many different types of approximations are done to make it more easier for you. So, the ab initio methods, GMS is one software, another one is called the Gaussian. So, if you are planning to use ab initio, these are the two softwares you will come across, the gamers and the Gaussian. So, semi empirical you have a lot of parameters, just like in our force field molecular mechanics we parameterize many things. So, semi empirical methods parameterize the Hamiltonian by fitting it to the experimental data or the results of the first principle, that means ab initio methods. So, these calculations are less demanding but less accurate. They cannot be applied to systems which are radically different from those used in the parameters. Just like your molecular mechanics, we cannot use, although we can sometimes use it, but the accuracy wise they are not really very accurate, okay. But it can be used for different systems, but too much different, then it is not correct. So, we can use semi empirical methods for calculating heat of formation, ionization potentials, okay. So, if I ionize a molecule, what is the energy required, optical spectra, electrostatics. So, lot of these simulations can be done using semi empirical methods, that is the advantage of these type of methods. So, many things are parameterized, that is how the method becomes simpler, less computationally intensive, faster, and we can go up to hundreds of atoms because many systems here are parameterized, that is called the semi empirical method. So, we have the semi empirical molecular orbital method. There are many semi empirical molecular orbital methods, approximations which involve the neglect of 3 and 4 center integrals arising in the j and k terms of Hartree-Fock equation. So, we neglect 3 and 4 center integrals, okay. For molecules with large number of electrons, evaluation of these integrals can be computationally impractical. So, we neglect, okay, we take only 1 and 2. So, many of them are experimentally determined parameters or sometimes from ab initio calculations or used to compensate for the missing integral. So, if you neglect higher order integrals, you can approximate it from the parameter, okay, which are calculated experimentally or through ab initio calculation. So, these are molecular orbital methods, semi empirical molecular orbital methods. Such parameters are obtained from measured or calculated ionization potentials, electron affinities, spectroscopic equations and so on actually, okay. So, what are the useful results from, we can calculate molecular orbital energies and coefficient, we can calculate total electronic energy calculated from the sum of Coulomb's integrals, molecular orbital energies for molecular orbitals in a molecule. So, many things can be done. If I want to know what is the energy required from moving from one orbital to another orbital, okay, we can calculate using semi empirical method. We can look at lowest unoccupied molecular orbital energy, we can calculate highest occupied molecular orbital energy. So, all these can be done using these methods, okay. Total nuclear repulsion, that is nucleus repulsion, that energy can be calculated. Total energy, that is electronic energy, nucleus energy, all these can be calculated together and we call it total energy. Heat of formation calculated from heat of total minus heat of isolated atoms. We can calculate conformational energies. Partial atomic charges calculated from the molecular orbital coefficient using methods such as Mulliken population analysis, electrostatic potential fitting, all these, okay. We can calculate the potential atomic charges, that is the Mulliken population analysis. Electrostatic potentials we can calculate. So, from molecular orbital calculations we can do all these calculations. Dipole moment, okay. So, what is the dipole moment? We cannot use molecular mechanics, we need to have semi empirical mechanics to calculate dipole moment. So, there are many semi empirical methods, extended Huckel theory, complete neglect of differential overlap, they are called CNDO, CNDO1, CNDO2, CNDOS, intermediate neglect of differential overlap INDO, modified INDO, enhanced INDO, MINDO2, MINDO2-3, AMPAC, Michael Zerner's INDO, that is called ZINDO, okay. then modified neglect of diatomic overlap, AMPAC, MOPAC, Gaussian, then Austin model 1, AM1, AMPAC, MOPAC, Gaussian, parametric methods, PM3, AMPAC, MOPAC, Gaussian, Semi-Chem Austin model 1, AMPAC explicitly. So many different types of methods, and generally I would suggest if you can use these type of methods, the AM methods and PM3 type of methods. Of course, MOPAC is also used quite a lot. Okay, so all these methods, although are popular, generally you can stick to the ones which I have marked here. Okay, so let us look at some of these methods. So the time required for Hartree-Fock scales as n raised to the power 4, that is evaluation of 1 electron and 2 electron integrals. Okay, semi-empirical method speed things up, considering only the valence electrons, using only a minimal basis set, setting some integrals to 0. So it becomes n square to evaluate, whereas time required for Hartree-Fock ab initio methods is n raised to the power 4. So in semi-empirical method it becomes n square. It also uses simple formulae to estimate the values of the remaining integrals. Like I mentioned, you can have some, that is why it is called semi-empirical. So there are certain empirical relation, so which can help you to calculate, estimate the one's remaining integrals. Okay, so we take only the valence electrons. Okay, we take minimal basis set and set some integrals to 0. So the evaluated integrals are also parameterized based on calculations or experimental data, that is why it is called semi-empirical. So this compensates to some extent from the simplifications. It implicitly includes electron correlation neglected by HF, whatever we neglect we include that. Okay, so there are many methods, MNDO, AM1, RM1, PM6, so many different methods. As we can see, methods is developed over a period of time starting from 1990s going down to 2000s. Okay, so CNDO, that is complete neglect of differential overlap. Okay, it's 1965 the first CNDO was developed. Okay, then came INDO, intermediate neglect of differential overlap. Okay, so slight improvement. As you can see 67, then came 73, 1980. Okay, so as the time goes, improvements on these methods were developed, but the earliest is CNDO, that is 65. Okay, then came NDDO, neglect of diatomic differential overlap. Okay, came MNDO, AM1, PM3, SAM1. Okay, so as time goes, starting from 65, complete neglect of differential overlap between these electrons, and then methods started improvement, the intermediate neglect of diatomic differential overlap, and so on. Actually, you can see 2000s we have better methods, PM6, okay, which are big improvement, but still they are quite fast, unlike the ab initio methods. Then came INDO. Let us look at a little bit on each of these methods. That is the starting from complete overlap going to INDO, that is the intermediate overlap. Compared to CNDO, INDO allows different values for the 1 center 2 electron integrals depending on the orbital types involved, like SPD, etc. Okay, so it improves on that. It is more accurate than CNDO at predicting valence bond angles, but poor overall at predicting molecular geometry. Okay, it gives you good idea about the bond angles, but molecular geometry it is not very nice. Okay. Then came ZINDOS. This is a parameterization of INDO using spectroscopic data. It was first described in 1973 by Zerner. Then they went on extending it to include most of the elements in the periodic table. Most of the elements. ZINDOS is still widely used for prediction of electronic transition energies, oscillator strengths, transition metal complexes. So if you have some metals, we can think about using ZINDOS. Okay. ZINDOS results can be of comparable accuracy to those obtained with the DFT method. Okay, density function. method. DFT are called density function methods, which come under the ab initio category. Okay, it can be compared with that. So that is the beauty of this type of methods, if you have transition methods also into your molecules. Then comes NNDO. NNDO compared to INDO, NNDO allows different values for the two centered 2 electron integrals depending upon the orbital type S, P, D, etc. Okay. You have the AM1 Austin model 1, which was developed in 1985 by this group, and then we have the PM3, that is a parameterized model, again Stewart 1989. So AM1 with an improved parameterization, automatic rather than manual, large training set. So they used larger training set to get the parameters for this model. So AM1, like I mentioned, AM1 and PM3 are still widely used. They are quite popular. I would still recommend that you can use AM1, PM3 reasonably well for performing semi-empirical calculations with the large number of molecules. Okay. Then PM6, this came in the year 2007, as you can see. This is meant for improving handling of hydrogen bonds. Hydrogen bonds is a big challenge. So in order to do that, PM6 came into. So this was included in some softwares, Gaussian 09 and so on. So the information is obtained from this reference. Density function methods, these are it was first developed 1998, Walter Cohn, Nobel Prize in Chemistry for his development of this density functional theory. Okay. So based on the electron density rather than the waveform. Okay, density function theory is based on electron density rather than waveform. So he did not consider electrons as a waveform. They consider electrons spread out, more dense in some areas, less dense in some areas, and that is how now it's being electrons are being thought of. That is why he got a Nobel Prize, Walter Cohen, in the year 1998. So density function theory optimizes the electron density, while molecular orbital theory optimizes the wave function. So that is the big difference between both these methods. DFT optimizes the electron density, MO optimizes the waveform. So molecular orbital thinks of the electrons as a wavy thing, whereas small piece of a particle moving in waveform, whereas DFT looks at electrons as a spread out into big area, and in some places it is very dense, in some places it is not so dense. Okay, that is components of the Hamiltonian are expressed as a function of the electron density, rho itself as a function of r. Okay, r is as you know is the location. So function of a function composed of an exchange functional and a correlational functional. Variational principle can be also be shown to be hold Hohenberg-Kohn variational theorem. The correct electron density will have the lowest energy. Okay, the approach used to solve for the density is the Kohn-Sham self-consistent field methodology. This is how density function works. Let us not bother too much about the ab initio and density function methods, because like I said, in drug discovery, computer aided drug discovery, we do not spend too much time on ab initio methods because it is not practical to look at large molecules using these methods, because they are computationally intensive and very slow. So generally semi-empirical methods are followed if you want to look at certain properties of small molecules, mainly drugs or inhibitors. Okay. So density function theory, so you have the local spin density approximation. So the functional values can be calculated from the value of rho at any point, exchange functionals, okay, local density approximation, Slater, correlation functionals, generalized gradient approximation, functional values use gradient of rho, exchange functional correlation functions. The name of the density function method is made by joining the exchange and the correlation function into one word. Okay, so we have BPWN1. Okay, B comes from this. Okay, P W91 comes from correlation. So you combine, so different types of density functions you can have by combining the exchange functions with the correlation functions. Okay. So if you really need to have a good knowledge of these type of ab initio and density function methods, you may start using, but generally for very small molecules. More of this density function, okay. Hybrid density function methods includes they are not pure density but hybrid. Bakes 3 parameter function for exchange, 1 parameter models also are there, okay. Then you have B3LYP, most popular density function method. Okay. So how do the DFT compares to MO? Okay. Now DFT is an exact theory, unlike Hartree-Fock, which neglects electron correlation, but the functionals used are approximate. DFT calculates scale as n power 3, ab initio calculates at n power 4, whereas your semi-empirical calculates at n power 2. More rapid basis set conversions, much better for transition in metal complexes. Of course semi-empirical are a bit quite approximate. Known problems with DFT: not good at dispersion, hydrogen bonds are somewhat too short, over delocalizes structures, hard to know how to systematically improve DFT results. In molecular orbital we can keep increasing the basis set and level of theory, okay. So in DFT you do not know how to improve and further, okay. So semi-empirical methods, some of the electrons like I said are considered explicitly and reduces computational demand of the problem, okay. Okay, so semi-empirical methods are very popular and widely used because computationally less intensive and we get reasonably good answers. Of course it is not exact but reasonably good answers. Okay, so we will continue further on these quantum mechanics methods in the next class as well. Thank you very much for your time.